get started. Okay. So to continue the theme of this morning, which is sort of a more practical applications look at the theory we've been learning over the last couple of days, I'm going to be looking a bit deeper at how DKIST is going to do its data calibration. And by that, I don't mean we're going to look deeper into how a flat is calculated or how we're going to remove curvature from a slit in any given scan. What I mean is we're going to talk about how the data center gets the raw data from the summit and turns it into calibrated level 1 products ready for the science community to use. Because as Alistair has gone into already this morning, it's a really big job. And we don't just have a single machine running through the data and pushing everything onto an FTP site. That's not going to work. For some background, I'm the calibrations engineer on the DKIST data center project, which means that this responsibility essentially falls to me. I'm the one that takes your raw data and makes your level 1 for you. Now, the reason for talking about this is that a lot of what we're doing here is also talking about level 2 data, and to do that successfully, you need to know how the level 1 was created. You need to follow the provenance of that data from when it was taken on the summit through creation of level 1 into level 2. And any steps you miss along the way means that you now are missing information about the data that you have. What we're going to look at is a sort of end-to-end thing of how the data center gathers all the inputs it needs for doing processing, schedules the work, because there is a lot of work, actually goes about executing it and doing the processing, and then saving that ready to be distributed to the wider science community. And the first thing I want to hit on here, and if you remember one thing from anything I say, it's this. DKIST generates about 95 megabytes of data per second. That's the one thing I want you to remember. Now, I don't mean it makes 95 megabytes of data per second when it's running. That's not it. This includes nighttime. This includes when it's stormy on the summit. This includes when things are down for maintenance. If you time stretch everything out, then every second, there's another 95 megabytes of data from the summit that hits the data center all the time. Okay? What that means is that each thing the data center does has to run faster than that, or we can never keep up. We have to receive data from the summit at least that rate. We have to transfer it to our processing infrastructure. We have to do the processing. This doesn't include any reprocessing of the data. If you want to reprocess everything once, double that number. That includes transferring it back out to our main stores, creating an inventory catalog for you all to search, and then getting it out at the other end to people who want it. And that's likely far more than this, because there's going to be multiple people downloading multiple data sets all the time. What this means inside the data center is that we have to manage the internal transfers of around 650 megabytes of data every second. Day and night, weekends, holidays, doesn't matter. All the time. Now this is a pretty big number, right? But to give you more of an idea of what that means, I've got a MacBook sitting here. It's got a 250 gigabyte hard drive in it. In the time that Alistair was talking, it's already full, the whole thing. About 40 minutes, and that's it, it's blown out. Since we started the workshop on Tuesday morning, this data rate comes to about 18 terabytes in a little over 2 days. It's a fire hose. There's just so much of it. But we have to manage it. And so to the question that you were asking earlier, what sort of things do we have here? We're going to be running in one of CU's data center sort of computing spaces. The initial data center is going to run on about 1,400 cores, of which about 500 to 600 of those are just for calibrating the data. And that'll be 500 to 600 cores running 24/7. We're initially going to start off with about 8 terabytes of RAM, and somewhere in the region of 8 petabytes of storage space that will have to go up by about 5 petabytes a year, every year. To do this, we have, again, as Alistair sort of pointed on, a virtualized microservice infrastructure. What that means is we have lots of little services, each doing very small tasks and handing off to one another. What that does is it lets us do some clever things, like if there's a bottleneck in one task we're doing, we can spin up another 100 instances of processes that do that task, and it can clear out a queue much quicker. And then once it's all done, we can kill off all of those services so they don't exist anymore and keep going with things. It's a much more efficient way to use the, honestly, fairly limited infrastructure we have. We're using object storage systems. It's a type of file system that doesn't really use a sort of standard folder hierarchy because we just have too many files. Standard file systems are just going to grind to a halt when you start throwing millions, hundreds of millions, over the course of 10 years, billions of images at them. The file systems start to break down. And the team that's building this, although there are a couple of us that have scientific backgrounds, are mostly software and hardware engineers. Most of the data center team are not scientists. And neither should they be, really, because this is an infrastructure and technology project that is attached to the telescope. So getting back onto what we actually do for calibrations. Well, the data center really only does 4 main things. We have a big bucket that data from the summit falls into. We keep it in that bucket. We do things to it. And then we send it out to people. And what I'm going to be getting into is the third part here, processing it. Now, to do this, there's going to be some hopefully limited pieces of jargon that I'm going to explain because a lot of this comes from information technology and computer science. That's the sort of realm that we're looking in right now. But the first thing we have to do is gather all the inputs we need to calibrate data. And the way that's done internally in DKIST is using something called processing candidates. These are, think of them like buckets that image FITS files are dumped into. And each one of them corresponds to an experiment that was done for a proposal. So this bucket contains data for someone who wrote a proposal about flares. This one was a proposal where they were looking for sunspots. This was looking at prominences off the limb. And data is taken on the summit and assigned to one of these buckets, and these buckets fill up over time. Okay? Now, the data center doesn't know which ones we can work on right now because there's just data falling into all of these. Until at some point, one of them becomes locked. And that either happens because the summit says, we're done with this one, or something hasn't fallen into the bucket for 2 weeks, at which point we say, it's been long enough, it seems like they're not doing anything else and they haven't told us, so we're going to lock it and start working on things. Now, this processing candidate is really just like a row in a table, like a row in a spreadsheet, essentially. It sits inside a database, and it has a bunch of things associated with it. And these are things that you will end up seeing in the headers of the data that's sent out to you. Internally, we give it an experiment ID. It's associated with a proposal. It's also part of what we call an observing program. Think of that as like a list of instructions given to the telescope and the instruments to make observations happen. Move this way, start this instrument running at 10 frames per second, record for this length of time. It's like a list of instructions that's sent up. And at the end, a planned recipe count. A recipe in our parlance is essentially a calibration code. Okay, a recipe is the list of steps that you use to turn raw data into calibrated data. And how many recipes, how many calibration codes do we need to run on this? We have no idea at this point, because in the data center, this is the information we have. We don't know what's in there. So we have to start figuring that out. So what we do is we can look at our processing candidate, and generally these will just contain science frames. They won't contain any calibration frames taken on the summit, things like darks and flats and any polarization calibration data that was taken. So what the summit also provides us is a big table that says for the processing candidate you're looking at, which happened to be number 7, we also ran some observing programs on the summit that had calibration data that you'll need to go along with it. And so we know now that we need to get all of the data that fell in this bucket, as well as ones that were associated with these IDs. So all we're doing here is querying databases and putting together a whole bunch of different information. But we know that we now need the information from this observing program ID, which was 9, as well as 16, 17, and 18. So now we have some numbers. We still don't know what's in the data yet. Okay? And the long-term plan for doing this sort of work is to automate it all away. But at the moment, we can't do that because we haven't learned the lessons from early operations yet. And so the idea is that all of these associations and things will be done at least semi-manually. And what we're doing in the data center, because we're pretty much a Python shop up there, is that we're using Jupyter notebooks. Some of you may have seen this sort of thing before. It's a way to integrate text alongside executable code blocks to sort of guide someone through doing something. And it's also what Stuart will show you after the break. He'll be showing you some demos, stepping through some Jupyter notebooks where real code will be executed in real time. And what this notebook is doing is, that step of associating all of these things together. So we know that this is what we need to get. Now that we have our list of numbers to pull things from, we can start looking at frame inventory. This is a list of all of the frames DKIST has ever taken. It will very, very quickly hit 1 million. Within a year or two of full operations, it'll hit 100 million. Within a decade, it passes 1 billion. It's going to be a very, very big list. But what we can do is we can say which of these frames belong to these IDs. And when we do that, now on these frame cards, we have information about what was in the data, because these are created when the frames arrive from the summit. And when we look at them, we happen to see that, oh, 3 instruments were running. This is the first point at which we know anything. And we can also see that for one of those, it was given the task type of observe. That means it was taking science data. We can also see other ones that had calibration data in them. There were some darks, some flats, some gains in there. All good stuff. Now, because we know there are 3 instruments in here, we can split the frames apart by instrument. And now, in this sort of simple example, we can say that, OK, we're going to have 3 different calibration recipes to run, 1 for each instrument. That may not be the case once we actually start doing things, but let's keep it simple and just say it's 1 per instrument right now. So what we have is we will also have a separate database that lists all of the calibration recipes that we'll be able to apply to things. And for simplicity here, let's get rid of 2 of them and just look at 1. Okay? Let's pretend that we're just calibrating VISP data. So great, what have we got now? We've got all of the science and calibration frames we need. We've got the calibration code that we need to do the work. Do we have everything yet? No, there's still some more. What we now need are parameters to associate with these that contain information that did not come in the data. For example, there may be a VISP parameter that has a bad pixel mask in it. Maybe over time something has happened with the detector. Some of the pixels have degraded slightly. We know this, but this data didn't tell us right now. And so it's prior information that we pull out of our parameter store and associate with this job. Also, yesterday, Christian was talking to us about polarization of the telescope and the Mueller matrices that collections of optical elements have. It may be the case that this data set didn't come with any polarization data. And so we're just assuming that we use the matrices that were derived yesterday. Well, then again, we'd pull that out of our parameter store in more of a sort of general DKIST-wide thing, because that's something that would be used for multiple instruments. So now do we have everything we need? We think so. Okay? And so just to put it all together, we have that processing candidate at the start. That was that big bucket that all of the data was falling in. We have our recipe, our list of calibration steps. We have our set of input data. That's all the frames we need, plus any associated parameters that have to go along with them. And we can use that to create essentially a run of this whole thing. And what we do is we generate a message, and it gets sent off to our automated processing cluster. Okay? So at this point, a job has now started. Calibrations can begin. Hopefully you're getting some idea of the complexity that even just goes into getting this started. This would be for one job. There's likely to be somewhere between 20 and 40 of these things happening every day. On the other end, we have our processing system. And what we're using is a piece of open source software called Apache Airflow. It's called Airflow because it was developed by Airbnb to manage their scheduling system. But we're using it to manage the execution of DKIST calibrations. And the way it works is you point it at a computing cluster, and it provides the necessary infrastructure to take large jobs and send them out piecemeal to be worked on in various ways. But the message arrives. It came from the part we did before. And all that stuff that was in there is still in it. And the important thing that's in here is a list of which of the calibration recipes we're going to use. And our processing infrastructure knows all of the recipes. It knows all of these things. And it breaks it out into a list of tasks, because we don't run calibration scripts as a large monolithic structure that just runs start to end. We break it all up completely. The first task could be something like, okay, go to the main store and pull all of the data that we're going to need to do things. A later one here could be average all the dark frames together. One of the later ones could be create a browse movie of the work you've done and push it up to YouTube so that people can see it on the search page. And we split all of these things up, and they're all linked in ways such that this task, for example, cannot begin until this one is completed. And what this does is lets us parallelize parts of the calibration pipelines, because we have to. If we don't, we can't keep up. Remember, every second, 95 megabytes. We have to keep up. So a simple look at what the recipe might look like in terms of the data center is, first we say, okay, we're working on this job. That goes to one of our databases and says, this has begun. Then we transfer all of the data out of our main data store and create a copy of it on local scratch space that the compute cluster works on. The compute cluster doesn't work directly on our main data store. It's actually faster to transfer it out and have it work locally. Then it generates some IDs. This example calibration task includes everything you've heard over the last 2 days. And then later, we transfer what we made back into the main store. We make a movie. We make an inventory for you all to be able to search on it. And then we say, now we're done. Now, this is the simplified version of it. If we break it out, then that example calibration task becomes a whole list of other interdependent steps. And there's more if we push it over to the other side. Now we can see things like instrument polarimetry and the things we've been talking about over the last couple of days. This is what the current VISP pipeline looks like. And actually, the diagram you're looking at here, this list of boxes and arrows, actually comes directly from Airflow in our current processing infrastructure. This runs just now. So the way in which this works, if you think of the cluster, is that we have a number of machines that are built to do computing work. We have our main object store. This is where all the raw data is held. We have an automated processing scratch store. This is the local disk space that's attached to all of these machines. And then we have our processing support database. This is where all the things that we talked about at the beginning are stored, how we put jobs together. And so the work begins. The first thing we do is say we've started. So this machine picked up that job. It goes to our databases and changes the flag to say things have begun. Then the next job picks up, transferred data to the scratch space. And it happens to hit all of these things because it tells this that a job has started. It pulls data out of here and transfers it into our scratch space. Then the next job picks up. But it just so happens that generating an ID for the data set isn't a dependency of calculating darks. And so now what happens is our scheduling system sends out 2 jobs at once for the same pipeline. And that's how we speed things up internally. We don't wait for previous things to complete unless we absolutely have to. And then the calculation of darks is finished before this one is. So what happens is that now we can apply the darks, even though this earlier step's still happening, because we don't need the result of it right now. We'll need it later. And so the infrastructure is built in this sort of cluster parallelization way, just to keep things going along as quickly as we can. The documentation and provenance of all of this is something that has been, at least in my experience, has been something that's difficult to get a handle on in solar physics in the past. When you get data from a mission, how do you know exactly what they did to it? Well, missions tend to publish papers of their calibration steps. Doesn't tell you it's what they did to your run now. It might tell you what they were doing to data 2 or 3 years ago, but it's not easy to get relevant, up-to-date information on that sort of thing. We are going to change that. What's going to happen is that when we're developing calibration codes, every time there's a major change, we create a build, and that build is now the new suite of calibration software we're using in the data center. In that code itself, which is predominantly Python, we're going to embed Sphinx markup. It's essentially a markup language. And so our code will be pushed out to a code repository that contains all of our calibration codes. That code repository will be publicly facing and open, so you can literally go and see line by line the code that we ran in our data center on your data. We will then use that code for data processing, and we will create output frames. And in those output frames, in the headers, it will tell you the version of our code that we used to do it. What that will let you do is that when we create our build, all of that Sphinx markup with all of the documentation that's in the code will be pulled out, and we're going to use a service called Read the Docs for this. It's a fairly easy way to pull the markup out of code and create sort of a nice web-based documentation service. And we will have documentation in here that relates to every version of our pipeline. But you'll know which version was used on your data. And so you can see the documentation that existed for your data at the time it was taken, even if it was years ago and we're already 7 versions down the line. We'll still have all of the old documentation, fully version controlled and linked for you to look at. So you have our description of the algorithms we used, you'll have the order in which we applied steps to the data, and you'll have the actual code that was applied to the data itself. This again is all part of NSF's guide to being open data, open source, open to the community. We want you to see what we did. And if you think we did it wrong, tell us. Because it's a community. And that will be one of the great ways that we can hopefully make all these calibration pipelines better for the community. Okay? We're not going to come up with all of the best algorithms and best ways to do things. We're going to try. But if anyone has any better ideas down the line, that's certainly something we'll be happy to entertain. So all the data is run through the calibration pipelines, and we get to the other end. And this is a slide that you've seen already. I just want to go into it in sort of a little bit more detail. At the end, what we're going to create as our unit of data within the data center is a data set. Overloaded term, I know. But what will be in here is a collection of FITS files and this ASDF file, which again I'm going to sort of skip over. Stuart's going to go into that in much more detail later this morning. But what you'll see in here is the data for one processing candidate. Now, if you remember at the beginning, that was the bucket that held data that sort of met one experiment for a proposal. It will be split by instrument as well. And it will be split by broad wavelength band, like by the filter in which it was observed. And within there, you'll have, an average data set, you'll have your 130,000 frames or something, right? It won't be too bad. it'll be bad. And our mandate, what we're aiming to do, is to provide data that has as much of the telescope and instrumental effects removed from it as we are able to accomplish. There may also be some atmospheric effects removed. That's something that's still dependent on how far we're able to get before the telescope is fully up and running. But to the best of our ability, we're going to remove all of the effects of the instruments and the telescope itself. And so from the processing candidate we saw at the start, this is what we would get at the end. There were 3 instruments in there, so we end up with 3 data sets. So I've been talking for just under half an hour. That's another 180 gigabytes that has been delivered. And if we don't keep up with that, then no one ever gets any data, frankly, right? So again, to sort of go back, this is my last slide, but the whole point of talking to you today is to give you a more practical idea of how these things are actually going to be done. Again, a deeper dive into calibration. I didn't talk about any of the steps themselves because I think it's important, especially a lot of you are at a fairly early stage in your careers, that you understand the sort of technology and infrastructure that goes into providing the data that you're going to use, because we want you to trust the data that you get. We want you to understand that we've done everything we can to make it as good as we can. And we want you to be able to check on that too. That's why we're making all the code and documentation fully open. To just put our hands up and say, here's what we did. This is the best we could do. But at least you can see that. Okay, so thank you. And if there's any questions on this sort of stuff, I'll take those now. Yeah. Hi.
So I was just wondering for the calibration stuff, if you ever, I don't know how much input you had on like the hardware stuff, but I'm not sure if you ever considered using GPUs instead of many parallel CPUs.
Sure.
Just because of their capabilities of parallelizing images and the fact that they are overall cheaper than large CPUs.
Okay.
And stuff like that.
Good question. So the question is, given the large compute required for this, have we given any thought to using GPU compute infrastructure? Because it certainly comes with big advantages, particularly when you're working with images, right? And the answer is yes, we have given it some thought. My input into the computing infrastructure was in prototyping some of these codes and actually trying to work out how many cores and what sort of infrastructure we would need to be able to keep up with the data rate. There is currently a plan to have some GPU nodes as part of our processing cluster because the airflow system that we're using doesn't care what type of processor it's sending things to. It can work with GPUs just as easily if you give it the right instructions to do so. The VBI instrument is sort of the standard imager for DKIST and would actually be a huge driver of the data volume that we receive for the summit. But most of the calibration for VBI is going to take place on the summit because it generates so much data that we can't get it all off. Now, to do that, they have to run in essentially real time on the data buffer stream as it's coming out of the instruments. At the data center, we have the luxury of being able to do things at night. But on the summit, they have to essentially do it in real time. And so what they have up there is a couple of racks full of NVIDIA Titans to handle that sort of thing in real time. And the big issue with doing the VBI in real time is that there's a step called speckle reconstruction that Kevin just sort of touched on yesterday. The VTF instrument is also going to need to do speckle reconstruction on its data, and it will do so here at the data center. We are currently weighing up, do we just buy a couple of racks of NVIDIA Titans to do the same thing that they're doing on the summit and run those really, really heavy duty intensive steps that benefit from that sort of architecture through the GPUs. So it's definitely something that we're putting time and effort into, and yeah. it's not in the initial buy.
Yeah,
But,
well, that's
yeah.
understandable, because they're only just getting to that point where it's actually better than getting this.
That's right. Yeah, and you need to make sure you have the right compute. Like, don't do a bunch of memory transfers, right?
Oh yeah, of course.
And that's
That's the ball.
exactly, yeah. So we're definitely putting a lot of thought into it. Yeah, for sure. Yeah. Mm-hmm. Sure. Yeah, the question there is about how the user is notified when data that they had proposed for is available. That's what you're asking, right? Yeah. The design for the data center right now has two different options for how this can work. You can either ask to be notified as soon as data that you are involved with is available for download. It's been processed by the data center and made available. Or you can be notified about this on a sort of digest period, maybe once a week, because it may be the case that if some of your data is coming through, a lot of it is, and then we just spam you for a few hours as all of your stuff gets made available. And at the moment, I know the plan is to link it to the emails from the proposal tool. There may be other notification channels that come in later. At the moment, I think we just have email. But so you don't have to keep checking our search portal to see if any data you proposed for is available. We will, as part of the calibration pipeline, one of the last steps once we push everything back into the main store will be to send a message to another local microservice that says, look who the PIs and co-Is are on this, and send them an email to say, your data's ready now. Does that answer what you were? Yeah.
The corollary, how about the notification of the execution of the observation?
The question is about notification of the execution of the observations. That's something we've talked about, and it's not currently planned. Mostly because at the moment we don't know for sure that it's going to work first time. And we could send you a message like every 2 hours as we try again. You know, but at the moment it's not planned to send out a message to say we've started processing your data. I mean, it may be because of the way that we're utilizing our infrastructure. Just because your job is now running doesn't mean that it's running on all 500 of our cores. It could be running on 3 of them because the rest are all busy with other jobs. It could easily take a job a week to get all the way through because there's a ton of other jobs midstream going along with it. So just because you get a notification saying it's started doesn't necessarily mean it's anywhere near finished.